All right, everyone. Welcome to another week of the GBO Science Lunch Series. Today, our speaker will be our very own Natalie Butterfield. We'll be talking about the dense molecular gas in the galactic bar dust lanes. So take it away, Natalie.
All right, thanks, Jesse. All right, so today I'm going to be discussing some recent GBT results targeting gas that's in the galactic bar dust lanes. All right, so just to motivate, one of the reasons why we're looking at gas that's in the galactic bar dust lanes.
Okay, I'm in.
Okay, so most of my research from graduate school and at the beginning of my postdoc here at Green Bank has been studying molecular gas that's in the central molecular zone. So the central molecular zone is roughly the inner 200 to 500 parsecs of the Milky Way galaxy. The gas properties in this region are much more extreme than what we typically see in the galactic disk. So for example, the line widths are about an order of magnitude larger than what you see in gas clouds in the galactic disk. So we're seeing line widths that are about 10 kilometers per second, whereas similar sizes in the galactic disk might have line widths that are around 1 kilometer per second. So it's about an order of magnitude larger. The densities that we see in the galactic center are around 10 to the 4 to 10 to the 5, whereas gas that's in the galactic disk is typically on the order of about 10 to the 2 to 10 to the 3. We also see much hotter gas temperatures as well. So gas in the galactic center has temperatures that are around 100 or so Kelvin, whereas gas that is in the galactic disk is on the order of about 10 to 20 Kelvin. So the environment is much more extreme than anything we see in the galactic disk. Which raises the question, where do these extreme properties come from? Do we see either gas that is heated as it is flowing into the galactic center, or is it shocked when it reaches the galactic center? We're really not sure where some of these gas properties are coming from. So gas is suggested to enter the galactic center through the galactic bar. So as is shown in the Bally 2010, results. So you have gas that is in the galactic bar, which is on these X1 orbits. And then you have gas that's in the galactic center is on these X2 orbits, which is the smaller red box that's indicated on this figure. So the gas that is in the galactic center, these X2 orbits are typically perpendicular to the galactic bar, which is the X1 orbits. However, trying to observe gas that we observe in the galactic dust lanes. So these are observed in distant galaxies. So for example, in NGC 1300, we see these really bright dust lane features of gas that is flowing in from the galactic disk into the galactic center in this galaxy. And so based on our studies of the Milky Way galaxy, we would expect to see similar dust lane features in our own galaxy. However, one of the issues with trying to observe gas that is associated with the galactic bar dust lanes is due to trying to observe through the galactic plane. So you're trying to observe this inner region of the galaxy where you have tons of material in the galactic disk that can obscure viewing this inner region of the Milky Way. However, there have been strides to conduct a 3D orientation of gas that is in this inner region using position velocity space. So the figure that's shown here is from Sormani and Barnes, 2019, where they looked at the gas in position velocity space. So this is the lower panel here, where you can see the identification of the near side and far side of the galactic bar dust lanes as highlighted in blue and red respectively. So looking at the top figure here shows where they are oriented relative to the galactic plane. And so you can see this warping of the galactic bar dust lanes above and below the galactic plane. So this means that parts of the galactic bar are excluded from many surveys which target the inner region of the plane, so around latitude of about plus or minus 0.4 degrees. And so the warping of the bar means that several of these gas clouds aren't included in many surveys. So in the Swarmani and Barnes, they looked at the amount of gas that is flowing into the galactic center, and they suggest an inflow rate of about 1 to 2 solar masses per year. So for our study, we targeted 2 regions of the galactic bar dust lanes, and I will go over the summary of those observations and then indicate where we are targeting in these 2 pilot studies. All right, so as I said at the beginning of this talk, this is very recent analysis and research. The data presented here were taken at the end of January and the beginning of February, so about a month ago. We used a similar setup as the gas survey. We used the KFPA, so we targeted multiple transitions of ammonia, and at these frequencies, the resolution of our observations are about 30 arc seconds or so, which is roughly around 1 parsec towards the regions that we're targeting. We use Vegas mode 20. So this means that we had the 8 spectral setup per Vegas bank. And so we used 23.44 megahertz. So that's around 200 or so kilometers per second. We had 5.7 kilohertz resolution, which is about 0.07 kilometers per second. But in all of the data that I'm presenting here today, I binned the data by 10 channels. So we actually had about 0.7 kilometers per second resolution, which is still enough to see the hyperfine structure of the ammonia transitions. Okay. So the first pilot study that we conducted was towards the midpoint of the bar. So the figure that's shown here on the left was the ones that I showed earlier, where you can just see the orientation of the bar relative to the galactic plane. And then the figures on the right just show an inset of the region that we were targeting. So we were targeting roughly the midpoint of the bar, which is around 4.5 or 5 in galactic longitude. You can see the proposed beam size of what the angular resolution of our observations are, along with the proposed coverage of this pilot study. So we targeted the brightest region towards the midpoint, and at this location, the expected velocities are around 200 or so kilometers per second. All right, and then the second study that I'm going to be presenting on today was in the second semester, where we targeted gas that was towards the edge point of the bar. So this is around a longitude of about 8. And at this position in the bar, we would expect velocities of around 150 or so kilometers per second. And again, the relative GBT beam size for these observations is also shown in the middle panel on the right. So you can just see how good our angular resolution is compared to the previous 12 CO observations. All right, so some initial results from the midpoint of the bar. We do see detections of the ammonia transitions, and the velocities of these detections are around 200 kilometers per second, which is what we would expect for gas that is associated with the galactic bar dust lanes. Since we targeted the 1,1 through 3,3 transitions, I'm just going to show an inset of what those detections look like. So in the panel image here, I'm showing the 1,1, 2,2, and 3,3 transitions towards this region. So one of the things that we can see is that there is a lot of ammonia towards this region of the galactic bar. We're seeing numerous clumps and extended emission throughout this region that is relatively bright for the short amount of time that we used in our pilot study. Okay, so just some initial results from the 20B273 study of gas that is in the towards the edge of the galactic bar dust lanes. So we also detect ammonia at this position in the galactic bar. The velocities of these gas clumps are around 130 kilometers per second, which again is consistent with what we would expect for gas that would be associated with the galactic bar dust lanes. So the cloud shown here was previously detected in the HOP survey at about 2 arc-minute resolution. So it's a good consistency check to make sure that we are seeing gas ammonia 1,1 that was detected in previous studies, but at better angular resolution. In the 21A 190 study that I showed previously, those were new detections that were outside of the previous HOP study. All right, so some of the kinematics of the 1,1 emission. All right, so what we did was we targeted several of the brightest clumps in the 2 detections, so in the edge of the bar and the midpoint of the bar. And so what we found is that gas that is located at the edge of the bar showed much narrower line widths than gas that was towards the midpoint of the bar. So this is what is shown on the right side here. So in the top, you can see gas, the gas profile of the ammonia 1,1 towards the edge of the bar. And so in this region, you can see very narrow line widths and the hyperfine structure of the 1,1 transition. The bottom panel is showing the spectra of gas towards the midpoint of the bar. And so one of the things that we notice is that the line widths here are much broader than what we see in the edge of the bar. Right, and so to look at this across our different ammonia transitions, so like I said, we have the 1,1 through 3,3 transitions. We wanted to compare what these profiles look like across our different ammonia detections. So what we're looking at here, so the black line at the bottom shows the 1,1 transition, the red line shows the ammonia 2,2 transition, and the orange line shows the ammonia 3,3 transition. For both the pilot or the midpoint of the bar at the top and then the edge at the bottom panel down here.
Natalie, do you think that that's because there's actually just a big collection of these clouds in the midpoint, that sort of each one is narrow, but the collection of them is, or you think there's still, your model is there's only one cloud in each
You mean
direction?
like if you had multiple components that could be blending it?
Yeah.
So that is a possibility to be able to disentangle if we had multiple components that could be just blended within our beam. We would need much higher angular resolution to actually see if we have multiple components that could be contributing to it. But right now with just the, within our single beam size, we're seeing much broader line widths. But again, yeah, that could be from multiple components that are just blended within that region.
I guess if you sort of inched your way from the outer edge to in, you would sort of start to see maybe multiple clouds, or not, I guess, but possible that would be a way of figuring that out.
Mm-hmm. Yeah, so that is one of the things that we would want to do, would be to make a moment 1 map and just see what the velocity field looks like. Because maybe you do have multiple components that might show up if you are looking at a map with the velocity field. Yeah, so this is mainly just some initial analysis that we're doing right now. All of the spectra that are shown here, we're using the same, I guess, same region size, which was the beam size, just to make sure that we were consistently comparing, what the kinematics are between the 2 regions that we targeted. But yeah, that is something that we would want to look at, would be going through some of the kinematics with a fine-tooth comb and seeing if we do have multiple components that might be contributing to the broader lines that we're seeing at the midpoint.
Yeah, thanks.
Mm-hmm. Yeah, so one of the things that we wanted to do with our spectra would be to fit using a fitting algorithm. In my case, I used the Python program PySpeckit. So PySpeckit, these spectra here were fit using just a single Gaussian, just to keep it simple. With the 1-1 transition, we might have the hyperfine components that could be contributing to the fitting or to basically the profile. And so what we wanted to do was just to use the higher J transitions where the hyperfine structure isn't nearly as strong as what you would expect with the 1-1 transition. So that's why I'm just showing the 2-2 and the 3-3 here. You can still somewhat see the hyperfine structures in some of these profiles here, but they aren't nearly as strong as what we observed in the 1-1 transition. Looking at what the fitting of the Gaussian profiles suggest is that in the edge point of the bar, so that's the panels that are shown here on the left, we're seeing velocity dispersions of around 1.5 kilometers per second. In the midpoint of the bar, so that is the spectra that are shown here on the right side, we're seeing velocity dispersions that are around 7. So we're seeing much broader line widths towards the midpoint or gas that's in the midpoint than what we're seeing in the edge point of the bar. Okay, so just to kind of compare some of our initial analysis with what we observe in the galactic disk and what we observe in the galactic center. So the line components that were, or the spectra that we're observing in the edge of the bar is much similar to what we observe in the Milky Way disk clouds. So the figure that's shown here on the right is from Kaufman 2017, where they show a comparison of CMZ clouds to galactic disk clouds. So the green points are showing the velocity dispersion as a function or for different radii. And looking at the edge points, we're seeing similar kinematics to what we would observe for the Milky Way disk clouds. However, with the gas that's towards the midpoints of the galactic bar dust lanes, we're seeing the higher velocity dispersion, so around 7 or so, which is much similar to what we would observe with CMZ clouds. So this could suggest that as the gas is accreting into the galactic center, we're seeing broadening of the line widths. But again, this could be caused by having multiple components towards this region that are blended along the same line of sight and within our beam size. So higher angular resolution observations would be needed to determine what the kinematics are doing at this higher resolution. All right, so future work. So one of the things that we wanted to do with our study that we just haven't had a chance to work on quite yet is to measure the gas temperatures. So since we have the ammonia 1,1, 2,2, and 3,3, you can estimate what the gas temperature is by fitting those multiple components using a Boltzmann diagram. And that was one of the things that we wanted to do. And that is what we're planning on doing over the next couple of months, is to use the detections that we have to measure the gas temperature and then compare those to gas that we observe at the galactic disk versus gas that we observed in the galactic center. We also recently proposed for some additional regions in the galactic bar dust lane. So those are identified in that bottom figure. So we requested 90 hours from this past February proposal call for the GBT to detect or determine if, if there is ammonia gas in this region of the galactic bar as well, and does this show similar either line widths to what we observe at the midpoint or the edge point, or is it an in-between? Do we see gas velocity dispersions of around 3 or something? So we have recently proposed for those, and so we plan to use a similar setup to observe those regions as well. All right, so just some simple takeaways. So we detect ammonia 3,3 in both the midpoint and the edge point of the galactic bar dust lanes. We have some new detections of ammonia that were not previously detected in any other ammonia surveys of the galactic plane. And so that's the figure that was shown here. On the left is the gas that's at the midpoint of the bar. And at these lower latitudes, this region of the galactic bar was excluded from several surveys. And so these are new detections of ammonia that have not been previously detected before. The initial analysis of the spectral lines at the midpoint and edge point of the bar suggests that gas towards the midpoint is showing broader lines than gas that we observe towards the edge of the galactic bar, which could indicate that that maybe the gas in the galactic bar is the missing link between what we observe in the galactic disk and what we observe in the galactic center. All right, and I will stop there and take any questions.
Okay, awesome. Thank you so much, Natalie. I'll first turn it over to the audience. If anyone has any immediate questions they wanted to ask Natalie, feel free to unmute yourselves.
I have a comment, I guess. If you go back one slide, Natalie, just to just looking at the line, the bottom plot there.
Mhm.
To me, almost that structure going from C towards A looks kind of like the spiral pattern you get in a disk that's, in a jet that's rotating. It's that's what you get if you have that sort of spiral. You see those knots. I don't know if that actually has in any way makes any sense, but that's still what it looks like to me. As if there was something that was illuminating or sort of causing a pressure increase that caused those, some phenomenon underlying this. I'm not aware of it, but it certainly looks like that's what it looks like to me.
Okay.
So are you planning to use the various ammonia lines to get a temperature profile, and so you can then would be able to pull out the non-thermal parts in the very center of the bar versus the outside? And that might
Yes.
tell you some of the dynamics going on.
Mm-hmm. Yeah, so that is the goal, is to fit the lower ammonia transitions. However, if you only have 3 data points in your Boltzmann plots, then your error bars are much higher. So one of the thoughts that we had was, with some of the future studies, to maybe attempt to include some of the higher J transitions. Like, I think using Vegas mode 20, we can get up to the 5-5 line. And so maybe tweaking some of our spectral setup to target some of the higher ammonia transitions instead of, for example, the HC5N that they had with the gas study. So mainly trying to target as many of the ammonia lines as possible to be able to get a better fit on the gas temperatures. But yeah, we want to fit the gas temperatures going forward.
So a question I have is related to your proposed region. After that point, do you have any intention of continuing, specifically with the other side, the red-shifted component of the bar, or is that too obscured?
So the far side, the issue with that is, like, I guess observing it with the GBT, since the galactic plane is tilted, and even at the galactic center, you're already pushing a very low elevation. So that's one of the reasons why we were targeting the near side, is because you would have a higher elevation at the GBT site, and it would make it a little bit easier to observe. We do want to fill in our pilot study and do a full survey of gas along the entire galactic bar. We've mainly been targeting some of the brighter regions just to get an idea of how bright the ammonia can be before going in and asking for a few hundred hours. So we've been building our study as we go, but yes, to be able to observe the full galactic bar and be able to identify ammonia clouds that are associated with the galactic bar and how the properties change as you're accreting into the galactic center is kind of the future goal.
Thanks.
Mhm.
If you go back to your concluding slide with the very nice, those are very nice maps. I think they look great. You sort of read the temperature. So the one line sort of, when that's a peak, you're sort of at 20 Kelvin or less. You can't really measure below 20 Kelvin with the H1 with the new ammonia because there's not another line to cross over.
Mhm.
And then when the 2,2 is brightest, then you're sort of at 50 Kelvin. And then when the 3,3, then you're sort of at, I think, somewhere between 50 and 100. I don't know exactly where, but that's sort of you can read the cloud temperatures off of those three a lot, really.
Yeah. Yep. Yeah. So you can get a rough estimate just looking at the three different J transitions. But I wanted to, I guess, have a Boltzmann plot versus just giving hand wavy values. But yeah, you can kind of, get an estimate on how hot you expect these clouds to roughly be.
Yeah.
Or at least a little.
The trouble actually really is with the Boltzmann plots is that you actually measure different clouds for each of the different lines. So you'll actually never get one temperature. It'll actually, like the 5,5 is gonna, when you add that in, you're gonna get a hotter cloud because you'll only be seeing the hot clouds that are whatever temperature that is, maybe 200 Kelvin, I don't remember. But so it turns out really the real trouble is trying to use an isothermal source model is what the real problem is. It's sort of, I really think we ought to be developing a real cloud model that is cold at the middle and hot on the edges or vice versa, whichever it is, that actually is not isothermal, but sort of typical, and I certainly haven't done that, but I always thought that that's what the real problem is with using those Boltzmann plots is they're trying to fit a isothermal model to something that has a temperature gradient in it. And that sort of,
yeah, I've seen that a lot with ammonia fitting towards gas components that are in the galactic center, where usually they'll do two temperature fits, where you have a hot component and then a cold component that's typically fit with the lower J transitions, and then maybe 6+ is usually fit with the hotter components as well.
So and that's obviously good as far as it goes. It just turns out somebody who is a powerful theorist ought to just find out what a ammonia cloud in a hot bath that's cooling is, and whatever that profile is would then be somehow. And I don't know how many parameters that would have. Probably that's the trouble, is I have so many parameters in the cloud model. But sort of just doing the isothermal fits is interesting because it can show you the cold spots inside of an otherwise warm cloud. And sort of it's a density weighted thing.
Yeah.
Well, Glenn, sounds like maybe you're proposing to lead such a project.
Well, no, I'm proposing to. I actually, unfortunately, at the NSF, I'm only proposing to fund such a project. So, so that's where the sad situation. I can't do anything useful. I can only suggest that it might be needed to be done. But that's great. It's a very good talk. It's good. Thank you. I'm excited by the prospect of it. You get sort of, when you do 1,1, you also get HC7N too. I guess, did you just ignore that data? It's sort of right beside the one, maybe I'm confusing it, but I think it's the HC7N is there too. You have to like find it and look at it, one of the lines.
Yeah, so we targeted, we targeted a lot of the similar lines that were in the gas survey. I know that they specifically targeted several of the, I think it was HC5N and HC7N. We didn't see anything in the pilot studies that were associated with those lines. at least that was bright. Maybe if we comb through and maybe if we bend, you know, some more channels, maybe we could get something or see something. But you know, in the initial pass through of what is, you know, what do we detect? You know, what are in our spectral windows? It was mainly the ammonia transitions that just stood out. So we've kind of pursued those first, since that was mainly what we were targeting in our proposal. But we do have several spectral windows that targeted those other lines that could have detections too.
Oh, thank you. Thanks. That's great.
Mhm.
Yeah, considering the presence of ammonia and the temperatures involved, you'd think there's some very fun molecular components to the gas here.
Mhm.
Don't know if anyone has proposed any studies or performed any past observations on them, but future ideas.
Yeah.
So does anyone else have any final questions for Natalie? Sounds like that's everything people wanted to talk about for today. So yeah, thank you again very much, Natalie. And though it's a virtual audience, so we can't give you a loud round of applause. That was a really fun talk. There we go. So anyway, thank you guys all for attending. And next week, we will have speaker Evan Smith. We'll be talking about RFI mitigation with Green Bank data. So take care, everyone.
Thanks.